very good evening. My name is Muhammad Slami Kamaruzama and my metric number is 24101238. And these are my teammates, Rehan Kavi Yaakob and also Hafiz Nabi Zamri. And today we are going to present our group assignment for semiconductor physics, which is doping process for extrinsic semiconductor materials. So as an introduction to everyone, we have prepared a crystal structure for a silicon substance, which can be seen here, which is in a diamond, same as a diamond lattice, which has two FCC primitive lattice. Okay, so before I start what I'm going to present, I just want to give general knowledge for what is doping. So for those who don't know, doping is a crucial process in semiconductor fabrication, particularly for creating extrinsic semiconductors by introducing impurities into the pure intrinsic semiconductor materials to modify its electrical properties. Okay, that is the basic introduction for what is doping lah. Before we continue to the second part, which is this one. Okay, so we have prepared two pictures actually on doping. So doping is basically, in short term, is adding impurities to semiconductors to improve conductivity. So it can create two types, which is N-type and P-type. So what is actually the purpose of doping? The primary goal of doping is to increase the conductivity of a semiconductor by introducing additional charge carriers. There are two types of doping, as I said earlier, which is N-type and P-type. So for N-type doping, it adds donor impurities that provide extra electrons, negative charge carriers. So for P-type doping, it adds acceptor impurities that carries holes. It is positively charged carriers. So the difference between N-type and P-type is basically the charges, which is for N-type it is negatively charged, and for P-type it is positively charged. Okay, so common semiconductor materials, they are basically used that around us. There are three I would like to name, which is silicon, germanium, and gallium arsenide. So these three are the common one known. So moving on. Okay, this is basically what I explained just now in table. So the N-type is the donor and the P-type is the acceptor. And also these are the types of N-type, the example for N-type and P-type, which is N-type at electron and P-type at holes. So there are actually three types of dopant for N-type semiconductors, which is elements with 5 valence electrons, or we can call it pentavalent, such as phosphorus, arsenic, and also antimony. So for P-type, elements with 3 valence electrons, trivalent, such as boron, aluminium, and gallium. So for doping technique, as you can see here, there are actually quite a lot, but we only chose two, which is diffusion. Diffusion meaning heating to add dopant. So the process to add the dopant is by heating the material itself. So the semiconductor is exposed to a dopant gas or solid source at high temperature, typically 800 to 1200 degrees Celsius. Dopant atom diffuse into the semiconductor lattice due to a concentration gradient. So what is actually the advantages of diffusion? It's basically simple and widely used for surface doping. And the application we can find, which is formation of junctions in silicon wafers. So the second one is ion implementation. So some of you may ask, what is actually ion implementation? So it's basically injecting dopant precisely, which is in a simple conclusion. But in the process, dopant ions are accelerated in an electric field and implemented into the semiconductor. The depth and concentration of the dopants can be precisely controlled by adjusting the ion energy and dose. So what is actually the advantages of using ion implementation? It is highly precise, and also uniform. So what is actually the disadvantage of using ion implementation? It requires post-implementation annealing to repair lattice damage. So there is actually two or three more techniques that can be used for doping, but we actually chose only two, and these are the pictures as you can see. For on the left side, you can see the diffusion. On the right side is ion implementation. Okay, these are the application of doping. It is used in diode transistors and solar cells, which are actually you can see around us, especially solar cells. And if you're in the engineering part of electronics and electrics, you can actually see it every day lah in diodes and transistors. So there are also other applications, but these are the simpler ones. So in summary, this concise summary covers the essential aspects of doping processes for extrinsic semiconductor materials. Uh, that's all from us. Thank you very much.